A satellite passes over a city twice, weeks apart, and from hundreds of kilometers up, it can detect that parts of the ground sank by a few millimeters, not with a camera, not with magic, with radar waves and phase math. So how does InSAR work? And what can it actually measure? Watch the phase. Each rooftop gets a sine wave tag. As zones sink by millimeters, the wave's phase shifts. One color wheel spin equals one full 2-piece cycle, our ruler for tiny distance change. In this video, you'll learn radar interferometry, InSAR, in plain English, what SAR is, what an interferogram really shows, why you see fringes, what coherence means, how scientists separate topography from motion, and where this is used in the real world, subsidence, groundwater, volcano inflation, earthquake deformation, landslides, and infrastructure risk. Against all oddities, Xiaom. Case File 004. Space and Science Mysteries Explained Like an Engineer. Here's the mystery. Earth moves in tiny amounts all the time. Here's the tool. Radar satellites that can measure those tiny changes from orbit. InSAR stands for Interferometric Synthetic Aperture Radar. In one sentence, InSAR compares the phase of radar waves from two satellite passes to estimate how the distance between the satellite and the ground changed, often by millimeters to centimeters, along the radar's line of sight. If that sounded abstract, good. We'll make it concrete. First, SAR. Synthetic aperture radar satellites transmit radio waves and measure the echo. Because they bring their own signal, SAR works day or night, and many radar wavelengths pass through clouds far better than visible light. But SAR isn't only recording brightness. It records amplitude, how strong the echo is, and phase, the timing of the wave cycle when it returns. That phase information is the secret ingredient. Think of radar like this. The satellite sends out a repeating wave pattern. When the wave bounces back, the sensor can tell where in the wave cycle it landed. That where is phase. Engineers note, amplitude tells you something about surface texture and geometry. Phase tells you something about distance. InSAR is a distance change tool wearing an image costume. Quick checkpoint. SR sends a wave, receives an echo, and records both strength and phase. InSAR uses the phase difference between two passes. Imagine a satellite passes over the same area twice from nearly the same orbit. Pass 1, it records phase for every pixel. Pass 2, it records phase again. Now we ask one question per pixel. Did the path length from the satellite to the ground change? If the ground moved upward slightly, the distance to the satellite changes. If the ground sank slightly, the distance changes. If the satellite's position differs slightly, the distance changes too. InSAR is the engineering process of isolating the ground moved part from everything else. When you subtract the phase from pass 1 and pass 2, you get a phase difference map. That map is often shown as colorful bands called fringes. Those fringes aren't decoration. Each cycle of color represents a full 2p phase change, basically one full wave cycle of difference. Here's the practical interpretation. Closely spaced fringes mean the phase is changing rapidly over space, which can indicate sharper gradients in deformation or complex geometry. Widely spaced fringes mean smoother change. But there's a catch. Phase is wrapped. It repeats every cycle. So raw interferograms show repeating bands, not a clean displacement number. That's why scientists do phase unwrapping, turning repeating cycles into a continuous estimate of displacement. Phase differences come from multiple sources. Two of the biggest are: 1. Topography. Mountains and valleys change the distance to the satellite. 2. Deformation. Actual ground motion between passes. So how do you separate them? You model and remove the topography using a digital elevation model, a DEM, basically a best estimate of the terrain height. Once the topography contribution is removed, what remains is closer to deformation, plus noise sources like atmosphere and decorrelation, which we'll get to. This is why SAR processing is a pipeline, not a single trick. Engineers note, if someone shows a movement map without explaining the processing, assume it's a draft, not a final measurement. Another key detail people miss: SAR measures movement along the radar line of sight. Distance changes between the ground and the satellite. That means, if the ground moves directly toward or away from the satellite, you see it strongly. If the ground moves sideways in a direction the radar is less sensitive to, you see less. If you want full 3D motion, you combine different viewing geometries, like ascending and descending passes, or add GNSS GPS ground data. This is why you'll hear line of sight displacement. It's not a weakness, it's the measurement definition. Quick checkpoint. SAR primarily measures line of sight distance change. To estimate full motion, you combine different looks or use ground truth data. Now the biggest practical limiter: coherence. Coherence is basically a measure of how similar the radar scattering is between the two passes. If the surface changes a lot, like vegetation moving, crops growing, snow changing, wet soil drying, then the radar speckle pattern changes, and phase comparisons become unreliable. High coherence tends to happen in urban areas, bare rock, deserts, stable ground, certain ice surfaces. Low coherence tends to happen in dense vegetation, forests, agricultural fields, rapidly changing surfaces, water. This is why you'll see clean SAR results over cities and messy results over forests, unless the time interval is short or the wavelength is chosen to help. Engineers note, SAR is not anywhere, anytime. It's where coherence holds. Even if the ground doesn't move, the atmosphere can change between passes. Water vapor and pressure conditions affect how radar waves travel. That can create apparent phase shifts that look like deformation. So SAR processing often includes filtering, time series analysis across many passes, atmospheric correction models, and sanity checks against known stable areas. In other words, one interferogram can be interesting, but a time series is more trustworthy. Let's talk about why this matters. Land subsidence. In many regions, groundwater pumping, soil compaction, or resource extraction can cause land to sink gradually. That sinking may be too subtle to notice day to day, but it can damage roads, pipes, foundations, and increase flood risk. SAR is one of the best tools for mapping subsidence patterns over large areas because it's wide coverage, repeatable, and sensitive to small changes. If you want a high RPM engineering audience, this is gold. It connects space tech to civil infrastructure and risk. Volcanoes can swell as magma moves and pressure changes underground. That deformation can be a useful monitoring signal. InSAR helps by mapping broad uplift patterns across a volcano's flanks, sometimes revealing deformation that's hard to capture with sparse ground sensors. Important caveat: deformation does not automatically mean eruption. It's one input among many. Engineers note, InSAR doesn't predict eruptions. It measures deformation that informs monitoring decisions. After an earthquake, the ground can shift by centimeters or more, sometimes over huge regions. InSAR can produce a deformation map showing where the ground moved toward or away from the satellite, often with striking fringe patterns. These maps help scientists estimate fault slip, understand rupture geometry, and refine models of stress changes. This is one of the clearest wow moments. A spaceborne radar system reveals a quake's fingerprint on the surface. Not all movement is dramatic. Some slopes creep slowly before catastrophic failure, especially when geology and water content change. Time series InSAR can help identify zones of persistent slow motion. It's not a guaranteed warning system, but it can prioritize where to look, where to instrument, and where risk may be increasing. Engineers note, InSAR is excellent for screening and mapping. It's not a replacement for on-the-ground monitoring when stakes are high. Let's summarize the pipeline like an engineer. Step 1. Choose two or many SAR images with similar viewing geometry. Step 2. Precisely align them. Co-registration. Step 3. Compute the interferogram. Phase difference. Step 4. Remove topographic phase using a DEM. Step 5. Unwrap phase to get continuous displacement estimates. Step 6. Filter and correct for atmosphere where possible. Step 7. Validate with coherence checks, stable reference areas, and ground data when available. Step 8. If you want reliable trends, build a time series across many passes. That's why InSAR results can be both powerful and nuanced. It's measurement plus careful processing. If you're watching InSAR maps online, here are 3 quick filters. 1. Is it line-of-sight displacement? If yes, don't interpret it as purely vertical motion. 2. Is coherence shown? If not, you don't know where the measurement is reliable. 3. Is it a single interferogram or a time series trend? Time series is usually more stable. Engineers note, the most responsible InSAR visuals show uncertainty, coherence, and processing context, not just a dramatic color map. InSAR compares radar phase between satellite passes to estimate distance changes, often millimeters to centimeters, along the radar line of sight. It's sensitive, wide area, and useful for subsidence, volcano monitoring, earthquake deformation, and slope creep. But it depends on coherence, and it's affected by atmosphere, so processing and validation matter. Subscribe for clean engineering-style science.